We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet up. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh?
When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 122 of the Space Rocket History Podcast. And now, Apollo, serious problems for the Lunar Module and Grumman. I want to begin this episode with testing. In 1965, NASA Houston reviewed Grumman's testing program to make sure it covered everything from small components to the biggest test articles. Here's a clip.
The only way pilots could practice maneuvering and landing the LEM was with flight simulators and awkward lunar lander rigs. Never before had a flying machine gone into actual service without a single test flight. But for the LEM, there was no other way. No other way, that is, than to test every system separately and together on the ground, every step of the way.
We tested at the component level, we tested at the assembly level, we tested at the subsystem level, and of course we finally tested it at the all-up level. And statistically, you couldn't prove reliability of the kind that we felt we had to have. So we adopted the policy that there's no such thing as a random failure. And that every failure had to be examined, had to be understood, and some action had to be taken to eliminate that cause.
On April 18, 1965, Grumman began test firing the ascent engine at White Sands. Here's the clip.
But in the urban confines of Long Island, the one thing Grumman couldn't do was the hazardous business of testing rocket motors. For this, they would need somewhere much more remote. In the early 1960s, the company went to White Sands in New Mexico. Here, in the middle of the desert, they built an engine testing facility. Lynn Radcliffe was the first manager.
When I came aboard that first day, I knew absolutely nothing about rocketry. It was almost as though I had walked into a foreign country.
The LEM was equipped with two very different rockets. The first, the so-called descent engine, would take the LEM from the command module down toward the lunar surface. It was an entirely new and untried piece of technology.
Up until this point in history, no one had ever built a rocket engine with a throttle. Either they were on or they were off. But in order to land on the moon now, you have to have a throttle so you can slow the spacecraft gradually to come in for landing.
This was an unbelievable maneuver when you stop and think about it. You're sitting on a column of thrust, just hovering there like a helicopter. And then as you let it go, the throttle a little bit, you lower it just at a few feet per second until you make contact.
Propulsion testing was also being conducted at Bell. Although engine firing programs were behind schedule, Houston expected better performance shortly. 6 lunar test articles, and that is abbreviated LTA, formed the backbone of the ground test program. Bethpage shipped LTA number 2 to Huntsville for vibration testing to see if it could withstand launch pressures. And LTA-10 was sent to Tulsa to check its fit in the adapter. LTA-1 was a house spacecraft used to iron out problems during fabrication, assembly, and checkout. 3 more LTAs were under construction. LTA-8 for thermal vacuum testing in Houston, and LTAs 3 and 5 for combined structural shakings, vibrations, and engine firings. Flight plans for the early production landers were flexible to accommodate schedule differences with the command module. LEM number 1 naturally received the lion's share of attention, since Grumman had to get it ready for an unmanned LEM alone mission, and that would be mission Apollo Saturn 206A. LEM number 1 would have to be ready at least 3 months before the Block 2 command module, or its first mission would be part of a test of the combined spacecraft. But Grumman was moving slowly. In the spring of 1965, John Disher of NASA's Washington Apollo office told Shea he believed LEM 1 would be a year late, which made the lander a pacing item. Many factors contributed to LEM 1's inertia, but ground testing topped the list. And the trouble in ground testing was getting equipment ready to make the test. Grumman's old problem, ground support equipment, had reared its ugly head. The significance of ground support equipment shortages was not lost on Washington. At a program review on April 20th, Miller told Houston managers to identify all lander ground support equipment along with the date it would be needed as a sort of thermometer to bring the weakness in the system to Grumman management's attention. In mid-May, Grumman officials looked at possible launch dates for the first vehicle, but could not decide anything definite because of a pinch in fiscal year 1966 funding. Hardware production had to be cut back in an attempt to absorb some of the loss. In July, Houston directed Bethpage to delete Lunar Test Article number 4, the vibration test article, and 2 flight test articles as well. To replace the flight test articles, 2 lunar test articles would be refurbished when they finished ground test. After trials with scale and full-scale models had been run at Langley and elsewhere, Houston also canceled a landing gear test model as an unnecessary expense. At a program review held on July 6th, Grumman asked NASA to relax the rules on qualification testing and to permit delivery to the Cape of vehicles not fully equipped. Of course, NASA manager Joseph Shea rejected this suggestion, ordering his subsystem managers to make sure that only all up, meaning complete landers, left the Grumman plant. Problems with some of the subsystems were a factor in this request. Bell, in particular, was having trouble with the redesigned injectors and tank bladders for the Ascent engine, and manufacturing problems were harassing Hamilton Standard's environmental control system. Subsystem manager Richard E. Mayo asked Donald Sullivan, head of a manufacturing unit in the Apollo office, to find out what was wrong. When he visited the Windsor Locks plant, Sullivan noted that although Hamilton Standard was turning out high-quality parts, good solid management in assembling and integrating the system was lacking. Design changes persisted throughout 1965. Electrical and electronics gear were also lagging. For example, the abort sensor assembly, which was part of the abort guidance system, was redesigned to incorporate continuous thermal control, a programmable memory for the computer, and a data entry display assembly. In mid-August, R. Wayne Young, who had succeeded William Rector as the Lander's project officer, ordered Grumman project manager Robert Mullaney to stop making changes if the present system could do the job. Program spending began to equal schedules in importance. Just as the Lander got rolling toward flight hardware production, it was caught in the budgetary squeeze imposed by Congress. Grumman had to shoulder most of the burden in holding expenses down. Expenditures had risen dramatically, from $135 million in fiscal 1964 to an estimated $350 million for 1966. As Apollo funding reached its crisis during spring and summer 1965, Grumman's fiscal discipline lagged in technical problem solving, subcontracting, and cost and schedule performance. To push Grumman toward a solution, Houston decided it was time to convert Grumman's cost-plus fixed-fee contract to an incentive agreement, with incentives to meet deadlines and penalties to face if they were not met. Grumman would be expected to overcome these deficiencies. The drive for incentive contracting had started in Washington in 1962, when NASA Associate Administrator Robert Siemens and John H. Rubel of the Department of Defense discussed the possibility of converting NASA contracts. The Defense Department had called for incentive contracting whenever possible for quite some time. However, the use of incentives rather than a fixed fee was a turnabout in government dealings with industry, and as such it was controversial. Critics pointed to lengthy delays in negotiations that tied up engineers who otherwise could be working on program hardware, and also a worsening of government-industry relations by causing contractual bickering. Siemens and Miller disagreed, insisting that incentives placed more responsibility on the contractor. It did take time and talent to work out the provisions, but it promised better performance. NASA had made only modest headway in the conversion between 1963 and 64, but the agency intended to revamp the spacecraft contracts in 1965. Miller wrote MSC Director Gilruth in April, stressing that incentives must reflect schedules, cost, and performance in that order to pave the way for incentive negotiations. Houston had to clear up a number of unresolved contract change authorizations, which would be reviewed by a board made up of Houston and Bethpage officials. The review began in mid-March and ended in April with participants deadlocked. Houston and Bethpage kept trying to work out the individual contract changes, but there was still no agreement in early June after 3 weeks of negotiation. Gilruth and Shea then discussed the impasse with E. Clinton Towle, president of Grumman, and decided that it was pointless to convert the contract at that time. Houston did impose a LIM management plan on Grumman, hoping to control cost, schedules, and performance. Until the last quarter of the year, Grumman would be allowed to spend only $78 million, which was less than the contract cost estimated during the unsuccessful review. If Grumman could stay within this limit for a quarter, however, negotiations for the incentive contract could resume. In the interval, Grumman concentrated on bringing its subcontractors into line and converting its agreements with them into incentive contracts, trying to demonstrate satisfactory control of the program. In September, Grumman submitted a proposal for contract conversion to NASA. Negotiations lasted until December and culminated in a contract with enough incentives to spur the contractor to maintain cost and schedules and to meet performance milestones. This arrangement, announced in February 1966, carried the lander program through 1969 at a cost of $1.42 billion. North America's incentive contract was also negotiated at an estimated $2.2 billion during the latter half of 1965. By 1966, the Lunar Module had achieved some degree of maturity. Grumman brought the lander out of the design phase and was trying to move it into the production line. But there were indications that Grumman was going to have problems. Control of in-house cost was fairly efficient. The company's chief difficulties lay in overruns by its subcontractors. R. Wayne Young, MSC's Lunar Module project officer, estimated that by the end of June, Grumman would spend $24 million more than it allotted funds. Moreover, since late 1965, Grumman's schedule position had been shaky, with delays indicated virtually across the board. In the light of these overruns, Houston sent a representative to Bethpage to discuss cost reduction measures. This conference produced a list of items to either be reduced or chopped from the major subcontractors. Meetings were then held with project managers at each of the subcontractors' plants to ram through cutbacks in requirements and manpower. The reviews, lasting a month and a half, culminated in tightened test procedures and performance requirements. To make sure that cost reduction measures were enforced, Grumman switched from quarterly to monthly meetings with its subcontractors, inviting the appropriate Houston sub-manager to attend. Despite these actions, Lunar Module cost still had not leveled off by late spring of 1965. In-house cost control and forecasting had also begun to deteriorate, aggravating the problems already encountered. Against this backdrop, Gilruth met with Grumman's new president, Llewellyn J. Evans, to discuss cost control and management of subcontractors. At Evans' request, Gilruth sent a management analysis group to diagnose and recommend ways to remedy the company's weaknesses. The NASA Management Review Team, headed by Wesley L. Jornovic of Houston, was composed of members from both Houston and Washington. Jornovic's team assembled in Bethpage in June. After a 10-day review, the team reported its findings to company corporate officers and NASA officials. Looking upon the Jornovic team as a personal management analysis staff, Evans promptly carried out most of its recommendations on program management, cost, subcontractor control, and ground support equipment. To make sure all orders were followed and all decisions were relayed speedily to the operating organizations, Grumman installed Hugh McCullough at the head of the Program Control Office. George F. Titterton moved from his vice presidential suite to the factory building that housed most of the spacecraft's managerial and engineering staff, thus ensuring a high degree of corporate-level supervision. To bring about the kind of cost forecasting and control that NASA wanted, Grumman adopted work packages, which meant breaking the program down into manageable segments with strict cost budgets and assigning managers to ride herd on each package. By linking task to manpower, program managers could better judge and control work in progress. This approach was a real departure from the commodity-oriented approach used by Grumman until that time. Joseph Shea watched these operations closely, and on September 19th expressed his belief to Evans that the work packages could control cost and might even affect some modest reductions. In the next 2 months, however, costs still exceeded budgets in most areas. Shea warned Tyterton on November 18th, unless discipline were enforced, the work packages could turn into so many worthless scraps of paper rather than effective management tools. Jornovik's team also discovered that no one person had been assigned responsibility for overall subcontract supervision. As a result, this whole area suffered from splintered authority. Grumman appointed Brian Evans to the newly created position of subcontract manager, reporting directly to the program director, Joseph Gavin. Evans then assembled a staff of project managers and assigned each to a major subcontract with jurisdiction over cost, schedules, and technical performance. The strengthened structure was a welcome tonic. Hardware deliveries improved and subsystem qualifications moved ahead. Tyterton also instituted quarterly meetings with presidents of the major subcontractor firms, similar to those held by Miller for NASA's prime Apollo contractors. The weakness in ground checkout equipment, which had been a millstone around Grumman's neck since the early days of the program, had developed because Grumman leaders simply had not recognized the immensity of the task. In February of 1966, Phillips pointed out to Shea that this equipment had paced the start of the propulsion system testing at White Sands. It had hampered in-house activity at Bethpage, and it threatened to delay operational readiness of checkout and launch facilities at the Kennedy Space Center. Shea replied that Grumman had put checkout equipment engineering and manufacturing on a 56-hour work week and was adding more manpower to the job. Despite Shea's reassurances and Grumman's attempt at remedial actions, the system failed to improve measurably. Grumman did make progress in engineering design, which was about 80% complete, but the bottleneck was fabrication. Phillips and Miller became thoroughly alarmed. They suggested that Grumman purchase components for the system from General Electric and other vendors who were having more success in the field. Subsequently, Grumman did put a variety of ground support items up for competitive bid. Back at Bethpage, the Jornovik team was having difficulty in assessing the ground support equipment problem due to the fact that Grumman did not have a coordinated plan. The team suggested that Grumman devote more attention to specific areas, such as deadlines for drawing releases, an intensified production effort, and a daily status review by program management. Llewellyn Evans named John Corson to oversee ground support equipment manufacturing and set aside a separate building for the fabrication workers whose numbers had grown considerably. Procurement was also strengthened, with Robert Brader heading a staff of a dozen purchasing people, and finally a ground support equipment command post was established to track day-to-day progress. Actions at Bethpage were complemented by moves in Houston. In mid-July, Wayne Young appointed a team to meet with Grumman every month to assess status and tackle problems. At the end of summer, with the last Gemini flight scheduled before the end of the year, Charles Matthews and William Lee shipped some surplus Gemini checkout items to Bethpage. Collectively, these measures brought a dramatic turnaround in Grumman's checkout equipment progress. As Gavin later observed, quote, "The tide was turned in midsummer. We were effectively on schedule in mid-October." End quote. Successfully overhauling management practices and fighting rising costs were commendable accomplishments, but the lunar module faced problems in other areas that were equally dangerous to Apollo. North American and the command module had been the big technical concern during 1965. Joseph Shea was determined that the lunar lander not follow in the footsteps of the Apollo command module. Echoing Shea's sentiments, William Lee commented that Apollo would be in deep trouble if the lunar module followed the pattern of Gemini and the command module. You may recall from previous lunar module episodes, there was a big question on radar versus optical tracking. In mid-1966, a significant hurdle was vaulted when the final decision of the radar optical tracker question was made. This was the lander's last subsystem to be settled. Engineers in the Manned Spacecraft Center, Apollo's office, and in Robert E. Duncan's Guidance and Control Division had promoted a contest that pitted the radar against the optical tracker, and performance trials took place in the spring of 1966. After tests and presentations by competing contractors, RCA versus Hughes Aircraft Company, a review board chose the RCA radar. Although both systems could be developed within the same time, and both cost $14 million, the radar had more operational flexibility than the less versatile tracker. The radar was heavier, but the weight had little influence on the choice because of Grumman's weight reduction program of the previous year. Perhaps the decisive factor in the selection was the outspoken preference of the astronauts. When asked by Duncan to support the contest, Deke Slayton stated forthrightly, quote, "The question is not which system can be manufactured, packaged, and qualified as flight hardware at the earliest date. It is which design is most operationally suited to accomplish the lunar mission." End quote. In light of recent experience, Slayton and Russell Swigert, the astronauts' representative on the evaluation board, believed that mission planning should make maximum use of Gemini rendezvous procedures and orbital techniques. They said this should include, quote, "an independent, onboard source of range and rate information, with accuracy on the order of that provided by the existing LEM rendezvous radar," end quote. So Grumman, which had slowed down radar development, shifted RCA back into high gear. The lunar module engines, too, were still having technical troubles that seemed to defy solution. For the descent engine, these included rough burning, excessive eroding of the combustion chamber throat, burning of the throttle mechanism pintle tip, where fuel and oxidizer met and combustion began, and difficulty in getting presumably identical engines to operate alike. Design engineers at the Thompson-Ramo-Woodbridge, better known as TRW Systems Group, made several changes in the pintle tip, the most significant being a change of the metal to a steel gray metallic element called columbium, which improved thermal characteristics. Other revisions included removing a turbulence ring around the interior of the chamber and realigning the flow pattern of the fuel that cooled the side of the chamber wall. Although qualification testing was delayed 6 months, the problem seemed to be solved. The asset engine technical problems were more fundamental. Bell was plagued by fabrication and welding difficulties and by severe gouging in the ablative lining of the thrust chamber. The injector, which had been fitted with baffles to combat combustion instability, encountered during the shape-charged bomb testing, was also a culprit. After an engineering review and resulting design revisions, including strengthening of the weld areas, Houston suggested that Bell begin work on a backup model. That would be expensive, but something had to be done. Subsequently, an improved injector demonstrated better burning characteristics late in 1966. However, another worry cropped up. At a Manned Spacecraft Center's senior staff meeting on November 4th, Max Faget reported 2 instances of unstable combustion. One during a firing test at White Sands with a flat-faced injector. The second at Bell during a bomb test for design verification of a supposedly improved baffled model. In both tests, damages had been extensive. At this point in the program, with the first 2 flight vehicles already late for delivery, these failures were ominous. Schedule difficulties for the Lunar Module were nothing new, of course. Grumman had been under the gun from the very beginning when the mode selection made the lander a late starter in the Apollo program. But during the summer and autumn of 1966, schedules became crucial. Here is a clip of Grumman manager George Skurla discussing Grumman's experience at Cape Kennedy.
Despite their indomitable spirit, at Cape Kennedy, the Grumman team were newcomers. They found themselves continually behind schedule, getting the unproven LEM into the flow, on the stack, and to the moon.
And we got into this environment down there where, with the Mercury and Gemini programs preceding our Apollo program, there were a lot of people in the Cocoa Beach and the Cape Kennedy area that were, you might say, well up on the learning curve and very experienced in the whole business of launching vehicles and manned space flight. We were the last large major contractor to come on the team at Kennedy, come on the stack, so to speak. And there was a lot of people who thought that perhaps we didn't have it, from experience and just general know-how to stay up with the crowd. The Cape operation was the last stop on the daisy chain. We at the Kennedy Space Center had the job of taking the ascent and the descent stage and putting them together and doing all of the pre-launch checkout of these vehicles, the ascent and the descent stages, and prepping them for launch.
In July, every vehicle on the production line through Lunar Module 4 was late. Moreover, because of tardy deliveries by vendors, a serious bottleneck was shaping up in the assembly of Lunar Module 1. By late November, however, the earlier remedial actions seemed to be having some good effect, and this continual slippage appeared to have slowed. At an October 6th briefing for Olin Teague's Congressional Subcommittee on NASA Oversight, Shea said that he expected the first lunar module to be shipped early in 1967. By the end of 1966, Lunar Module 1 and 2 were in the test stands at Bethpage, and Lunar Module 3 through 7 were in various stages of fabrication and equipment installation. But the coming of the new year did not yield the progress Shea had looked for the previous October. Toward the end of January 1967, it was revealed that Lunar Module 1 would not reach the Cape in February as expected. In short, the moon landing might be delayed because the lander was not ready. But the mission planners could not wait for the Apollo engineers to iron out all the problems. They had to plan for a landing in 1969 and hope that the hardware would catch up with them. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.